ladies and gentlemen, today we're going to learn about rotational kinematics. Alright, so to start us off, it's important to know the difference between radians and degrees. In rotational kinematics, we're going to be using a lot of numbers with radians as a unit. So if you take a look at the chart, you can see that radians is one full circle is 2 pi, whereas one full circle for a circle and degrees is 360 degrees, right? Now, not people know this, but radians is actually a unit and not a variable. Now, a variable is something that you put in the equation, whereas radians is at the end that describes the number that comes right before it. Alrighty? Cool. So, you might be asked to convert between radians and degrees, and here's an example of how. So if we want to go from 47 degrees to radians, if degrees is the unit on top, we need to eliminate the units on the top by dividing it by the units on the bottom. So we are essentially multiplying 47 degrees by a factor of 1. Now, what I mean by that is 2 pi radian is the same as 360 degrees. 2 pi radian is one full circle, and 360 degrees is one full circle. Now, if you plug that into a calculator, you get roughly 0.8203 radians. So we just went from 47 degrees to radians. And we could do the same if we were to go in reverse. For example, if we wanted to go from 4 radians to degrees, radians is the unit that's in the numerator, and so we have to multiply by 1 once again, and we have to get rid of the radians in the numerator by multiplying radians in the denominator and having degrees in the numerator, and we get 229.18 degrees. Okay, now keep that in your back pocket because there might be a couple of problems where we will have to do that. All right, so the whole idea behind this unit is this idea of displacement, or kinematics. Now, it's going to be a lot like what we did in the very beginning of the year with linear or translational kinematics, but now we're going into angular or rotational kinematics. And so we're going to be seeing a lot of the same vocabulary terms. For example, displacement is one of them. Now, displacement is the shortest distance between point A to point B. And in this case, we see that as delta R or delta S, okay? And that is the outside edge of the rotation. But if we wanted a angular displacement, we would say theta or delta theta, the change in the angle, okay, or the change in the thetas, right? So we are going to be able to convert from one to another, and we're going to be doing this a lot. And this is not a equation that you get in your equation sheet, so you should definitely memorize this. So I'm going to show you the equation, and I'm going to talk you through it in order to explain exactly how one goes to the other. So we have delta S, or the change in linear displacement, is equal to r delta theta. So if you multiply the angular portion by the radius, now the radius is something that is straight. That's how I like to memorize it. If you multiply something that is straight to something that is angular, you're trying to turn that angular thing into a quote-unquote straight or a linear value. And so if you multiply the radius, and the radius is always going to be a straight line, by something that is angular, you're making that angular thing straight. And so if you multiply radius times delta theta, we get the displacement, delta S. All right, and here we go with velocity. Okay, so linear velocity, or in this case tangential velocity, we know it as v sub t or v sub r, and the units are meters per second. Now, that v sub t and v sub r are special velocities. We call them tangential velocities, and I'll show you exactly what they are in a little bit using simulation. But in this picture, if we go from point A to point B, okay, so that has an angular displacement over a specific time, so displacement over time, we get velocity. Okay, and in this case, we have angular velocity, and the units are radians per second. And that fancy-looking W is actually the Greek lowercase letter omega. Okay, omega. All right, now here is how we can convert the linear or the tangential velocity, v sub r, which is in blue. Okay, and so that's a straight vector. That's not angular. Okay, and we get that by multiplying the angular velocity by the radius. Once again, the angular velocity is something that has angle, so not straight, by the radius, which is straight. So if we multiply a linear radius with something that is angular, you're turning that angular thing into a straight value. And in this case, it is the linear or the tangential velocity. Okay? All right. And here's an equation that is a bit longer, but let's go through this. So omega, or the angular velocity, is equal to the change in theta, or the change in the angle over time. Okay, much like linear velocity is displacement over time, Angular velocity is the change in angle over the change in time, okay? Because now we have to start thinking in terms of angles. And this 2 pi is one full circle, and f is the frequency, how often it goes around 360 degrees, or 2 pi. Right. And this v divided by r is just a rewritten version of v equals r omega. If we divide r by both sides, we get omega. And here's one way I like to think about it. V sub r is a linear value. Okay, it's straight. And if we want to take something that is linear or straight, we got to take out the straight thing out of it, and which in this case is the radius. So if we take the radius out of it, that linear thing turns into something that is angular. Okay, it's just something that I keep in mind because it helps me understand and memorize these equations. Okay, so this tangential velocity is a very unique concept. When an object is going around in a circle, okay, it has an angular velocity. In this case, the angular velocity is in red. Okay, so the change in the angle over time, but at any given point, it has what we call a tangential velocity. And that tangential velocity, much like the name, is tangential to the circle at whatever point it's at. So at point B, the tangential velocity is tangential, where it's only touching that one point of the circle, and it will always make a 90-degree angle. So right there will be 90 degrees. And so at point B, whatever object is at point B is moving directly to the left tangentially. So what that means to us is, let's pretend that we have an object on a string, and we are swinging around and around and around and around. And at point B, we let go of the string. So if we let go of the string, the object isn't going to keep on spinning in a circle because we're no longer pulling on it. Okay, but instead, what that means is as soon as we let go of that string, that object will move in a straight line. Okay, because that goes with Newton's laws. An object in motion will stay in motion unless there's an outside force. And if you're swinging an object around and around, the outside force is a string holding back the object. But as soon as you let go, it's going to go in the direction that is actually headed, which is what we call the tangential velocity. So if we are swinging the object around and around and around, and at point B we let it go, it'll fly straight to the left. Okay. Now here's a different example to show you exactly what tangential means. So at point B, the object is moving like down and to the left. Okay, that is its tangential velocity. However, its angular velocity is how fast it's going around in a circle. But the tangential velocity is how fast it's actually going if it were to be released at that point. I'm going to show you a simulation, and this simulation we are going to be working on in a class. All right, so let's take a look at this simulation. In this simulation, we have a ladybug, and in green, that is our tangential velocity. So if I push play, notice that the tangential velocity is constantly changing, okay? But it is constantly going, the direction is always going to be tangential to the circle, okay? And if let's say we speed up this little merry-go-round, all right, that means the ladybug will be moving faster. So the ladybug is moving faster. What that means to us is that not only is the angular velocity increasing, but the tangential velocity is increasing as well, because of the equation v is equal to r times omega. So if omega, or the angular velocity, or how fast it's spinning around and around, increases, the tangential velocity increases. So here I am, I'm going to increase the tangential velocity. So take a look at the arrow. We see that the arrow does in fact increase. Okay. Now, what would happen if we start spinning the object in the other direction? Well, the tangential velocity has to follow the direction that the object is spinning in. So if we were to make this ladybug spin in the other direction, so look at that, the tangential velocity also switches. Okay, and more importantly, it's still tangential to the circle, and it's still pointing in the direction that it should be going. Great. Now let's go back to the PowerPoint. When we are describing the direction of the angular velocity, we have a very special rule. It's called the right hand rule. So you're going to need to use your right hand. Okay. Now, it might seem silly, but if you don't know your right hand from your left hand, I highly encourage you to start writing R's on your right hand and your L's on your left hand, because there's many times where students during exams or during practice problems, they actually use the wrong hand for the right hand rule. Now, the right hand rule goes like this. If your fingers are curving in the direction of the motion, your thumb points in the direction of the angular velocity. So if we were to take a look at this picture, we can see that this picture, if this object were like flat on the ground, this object is moving counterclockwise. But in order to fully describe what is counterclockwise, physicists use what we call the right hand rule, and we see that the direction, we describe the direction as going upwards. Now, this isn't something that physicists made up, it's actually something that shows up in nature. And when we go into angular forces and angular momentum, we will definitely use our right-hand rule once again. And this special little rule actually it's pretty cool. It's something that nature follows as well. Okay, so practice with me. I'm going to go over a couple examples using your right-hand rule. Okay, so if the object were to be spinning clockwise, okay, spinning clockwise, so curl your fingers and make it go clockwise, okay, my finger is pointed down. My thumb is pointing down. So what we can say is that the angular velocity isn't clockwise, but rather down. The object's angular velocity is down, not counterclockwise, but down. All right. Okay, so if we were to have something like this, like the object is on its side, okay, this one is counterclockwise. So if I do this with my hand, I can see that my thumb is pointed to the left. And if we were to switch it, and it's gonna be a little bit weird, I'm trying to do my best here, but you get the point. If you break your arm and you dislocate your shoulder, you can see that the right-hand rule, the angular velocity is pointed to the right. Cool. So in this case, you are looking at an object straight on, like this is an aerial view, and the object is spinning definitely counterclockwise. Everything else was in like a different point of view. For example, you are kind of looking at this like from the side, and in this case, you are looking at the object when it's like upright. So in this view, you are right above the object. Okay, so if you're right above the object, notice how my hand changes, but the angular velocity is counterclockwise. So the angular velocity is counterclockwise. My thumb is pointing right at me. Okay, so the angular velocity is towards you, or in this case, out of the screen. And we draw that, we write that as a circle with another mini circle in the middle. Okay, it's kind of like you're seeing like your thumb being pointed right at you, or how I always saw it was if it was like a tiny little bug or like a gnat, then you're seeing that tiny little circle, that's the gnat flying right at your face. All right, now the next one is like, once again, you're looking right above the object and spinning clockwise. Okay, you're turning your finger, and my thumb is right into the screen. All right, and in this case, we designate that as a X, a circle with an X in the middle. And how I always taught it was, so imagine the gnat or the fly went and it like splatted right on the screen, and those are the X's above his eyes, or like that's like the splat that it made. Okay. All right, right hand rule. Make sure if you don't get the right hand rule, go back and get some practicing. Try doing the right hand rule with your hand until it matches the description. And this is something we'll definitely practice in class. And this entire unit will be using the right hand rules. Don't get lazy and get some practice in. Okay, so we covered velocity, and now we're going straight to acceleration. So acceleration was the change in velocity over change in time, units meters per second squared. But now we have the angular velocity, and the angular velocity is the lowercase alpha symbol. So alpha, or I like to call it the fishy, because if you draw it, it kind of looks like a little mini fish. This font kind of makes it look like an A, but when I draw it in class, it'll look like a fish. And the units are radians per second squared, because much like acceleration, linear acceleration, it was meters per second squared, we have radians per second squared. Okay, and so if we want to go from one to another, blue is the linear with the tangential, and red is the angular. Remember, in order to get something that is linear, we got to take something that is angular and apply something linear to it. And in this case, it'll be the radius. So we are doing radius times the angular acceleration, and we get the linear or tangential acceleration. That's how fast it's accelerating, okay? And once again, that's not in your equation sheet, so memorize it, all right? And another formula is the change in angular velocity over the change in time. Here we go. All right. So you might be thinking to yourself, there's a lot of similarities, and that's because you're right. There are tons of similarities. There's linear displacement, which we have delta x or delta s, and there's angular displacement, which is delta theta. All right, the change in the angle. Velocity we represent with a v, and angular velocity, that's the omega. It kind of looks like a W, and W kind of looks like a V, like in French. I think V is ve, and W is W, right? Like V and W, right? Okay, so I don't know, it works for me. Acceleration is lowercase a. Angular acceleration is that alpha, or that fishy symbol. Okay, it kind of looks like a fish. And of course, time, which I left as the black font, because time is universal. Okay, time doesn't care if it's angular or linear. Time is time. Cool. All right, moving on. We went through a lot of these conversion tables, but as you can see, there's a lot of similarities. Okay, if you want to go from angular to linear, right? So the blue is all linear and the red is all angular. If you multiply something angular by the radius, something that is straight, we get something linear. If you want to get something angular, you get something that is straight and you take out, okay, you divide out whatever the straight component is, and that will be the radius. All right, so take the time now, copy this down. Now this is not something that you'll be given on the equation sheet, so it kind of helps if you memorize it. Now the trick is if you memorize one of these equations, you basically have everything else memorized, right? So for example, if I choose to memorize velocity, tangential velocity is equal to radius times omega, okay, I can apply that same formula for acceleration. If I want linear acceleration, I multiply r times alpha, right? Or if I want the displacement, the angular or the arc length is equal to radius times theta, right? And this is just rearranging the equation to make it look like that. So, and the same applies. So if you memorize one, you basically have everything else memorized. All right, so here's where the fun begins. We have our linear or translational kinematics. This is back from our very first unit. We can use the same exact equations, but apply angular variables to get the same exact equations, but for angles. Man, physics is like really cool. So here we have, I'm gonna go to the second one. We have position, final position is equal to initial position plus initial velocity times time plus 1/2 acceleration times the time squared. Now everything that's in blue is linear. Okay, now anything that is position, we have angle. So final theta is equal to initial theta plus the initial angular velocity times time plus 1/2 times the angular acceleration t squared. So sometimes in class you might hear me say this as theta final is equal to initial theta plus initial omega times time plus 1/2 alpha t squared, right? And I think it just really sounds cool. So in your equation sheet, you're given these first two equations. Okay, with the AP equation sheet, you're given the first two, but you are not given the last one. But that shouldn't bother you because you are given this equation on the equation sheet. And if you know how to go from one to another, you have the third equation, right? Cool. So that, I think, wraps it up for our circles. If you want to see the cool mind trick at the very beginning of the PowerPoint, the spinning dancer, type that into your web browser and take a look at it. It's cool. So if you stare at it for long, it kind of looks like the dancer is going in one direction, but if you stare at it long enough, or like blink, it like she spins in the other direction. It's really mind blowing. Anyways. Study up, memorize those equations, and memorize those variables, and I'll see you next time.